Testing 1, 2, 3. Flipped classroom video for Maths A2 Unit 3 Trigonometric Differentiation. So we're going to look at the gradient of sine x and cos x to start with. Now you already know, if you've looked at differentiation from first principles, that if y is sine x, then dy by dx is cos x. If you haven't seen that yet, you will do. So you'll have to take this as read if you haven't seen the differentiation from first principles. We also know that if f of x is equal to cos x, then f dashed of x is equal to minus sine x. Now, there's a good way of remembering which way round these go, because that minus is a bit irritating. It means you've really got to remember what's going on. And if you can't quite remember, then a good way to think of it is to think of the actual graphs. So here we have at the top the sine graph in green to match the equation above, and the red is the cos graph. And if we look at the gradients, then for sine x at 0 we have a gradient of 1. At pi by 2 we have a gradient of 0, it's flat. At pi it's a gradient of minus 1. And then at 3 pi by 2 is a gradient of 0. For cos, we can see that at 0 we have a gradient of 0. At pi by 2 we have a gradient of minus 1. And then at pi we have 0 again. And at 3 pi by 2 we have a gradient of 1. And so what we can see by comparing the graphs is that the gradient of sine x is equal to the value of cos x. So at 0 we have that gradient of 1, and we can see that the red cos curve is at 1. And similarly for the gradient of cos we have minus sine x. So if we look at, say, pi by 2 on the red cos graph, we can see the gradient is minus 1, but the value of sine is plus 1, and so we have to negativize it, if that is a proper word. So that's a way of remembering which way round when we differentiate sine and cos. It's the cos when we differentiate it that gives us the minus sign. We now need to have a look at the gradient of tan x. Now again, you should have seen the quotient rule, or you've probably seen the quotient rule. If not, we're going to have a look at it anyway. So we could do tan x from first principles like we did with sine and cos, but it's easier to use the quotient rule. So differentiating from first principles is a difficult job, and so if we've got other techniques we do try to avoid it. So we can express tan x as sine x over cos x, which is of course a quotient or a fraction. And the quotient rule says that if we differentiate, or do d by dx of, that's the same as writing differentiate. If we differentiate a function u divided by a function v, then the quotient rule tells us we get v du dx minus u dv dx divided by v squared. Okay, so in this situation we're going to call the top of the fraction is u, so that's equal to sine x, and the bottom of the fraction is v, so that's cos x. And we're going to write down du by dx is cos x and dv by dx is minus sine x, which we've just seen on the previous bit, but it's good to have your u's and v's and du by dx and so on all written out clearly so that you can substitute them into the formula. So there is our formula again, and now we substitute everything in. So the d by dx of u over v becomes d by dx of sine x over cos x. The right hand side of v du dx is cos x times cos x, and u dv dx is sine x times minus sine x, and then v squared on the bottom is cos x squared. Okay, so the next line, well, cos x times cos x is cos squared x. Minus sine x times minus sine x gives us plus sine squared x, and on the bottom we wrote it as cos x squared before because we were subbing into the formula at the top, but of course we tend to write that as cos squared x. And we now remember that cos squared x plus sine squared x is 1, so we can write this as I should have said as well, we've replaced sine x over cos x by tan x on the second line from the bottom, which of course was what we were trying to do. So we've now got d by dx of tan x is 1 over cos squared x, and we need to remember that sec x is equal to 1 over cos x, and we therefore get d by dx of tan x is equal to sec squared x. Okay, now we should have a look at this now using the chain and or product rules, because all of these functions we can use those general rules for. So in this situation we've got tan of x cubed, and we have to differentiate that with respect to x, and simplifying your answer as far as possible. Now, that's a wording that's often used in exams, so it reminds you that if there is any tidying up to do, we need to do it. For this one, there isn't any tidying up. dy by dx is equal to 3x squared times sec squared of x cubed. So that's a chain rule because we have a function of a function, and we can look at each bit. So first of all, the inner function, which in the chain rule video we've called g of x, and your teacher may have done. There are different ways of notating it, but either way it's the inner function, so we have to differentiate that, which gives us 3x squared. Tan, well, we've just seen that when we differentiate tan we get sec squared, and then for the chain rule that would be tan is our f function, so sec squared is our f dashed, and of course it's got to be f dashed of g of x. And g of x was our inner function in the first place, the x cubed, and we therefore, in the differentiated function, we end up with sec squared of x cubed. So that's that example, and we'll have a look at one more example as well. This time we've got to differentiate with respect to x again, so same wording, but this time we have a function called f of x, and it's equal to x squared times sine of 7x. So this time we have a product rule because we've got the function x squared times the function sine of 7x, and we also have a chain rule because we have sine of 7x, not just sine of x. So let's have a look at what it comes out to. So it ends up as f dashed of x is 2x sine 7x plus 7x squared cos 7x. So where's everything coming from? Well, first of all, with the product rule we have u is x squared and v is sine of 7x. So we need v du dx, which we have on the left there, and we need to add that to u dv dx. And the reason there's a sort of dot coming from dv by dx to that blob is that you'll see that when we've differentiated sine of 7x, we've got the 7 cos 7x, and to write it tidily we've put the 7 before the x squared, which is the conventional way of doing it. So we have done a bit of tidying up as we've written it. I'll go through the bits so you can see how that's come about. So first of all, our v is just sine of 7x, so we've written that. Our du dx, which we've put before the v because of convention, is the x squared differentiated, so that's our u differentiated, giving us 2x. And then for the other half, what have we got? Well, first of all, the x squared, or our u, we just write down. Then we have to think about differentiating v, or sine of 7x. So first of all, we differentiate the inner function, which means differentiating 7x, which just gives us 7. And then we have to differentiate sine, which gives us cos. And finally, because that's a function of a function, or a chain rule, then that's cos of 7x, which was in the bracket in the original sine function. And so that's our answer. Now, we could perhaps simplify by taking an x out, but I'm not sure that would make it any simpler. So sometimes doing more tidying up won't make it any easier to understand, and that's one of those places where there's a bit of judgment comes in. So if you did take x out and then call it x times 2 sine 7x plus 7x cos 7x, you wouldn't affect any marks in the exam, but if you don't do that, you wouldn't lose a mark either. So unless there's a good reason to tidy up in that way, yeah, one can be happy to stick with that as an answer.